Thus far, we've seen how in input graphs without negative cost cycles, the Bellman-Ford algorithm correctly computes shortest paths from the source vertex S to all destinations V. But what about input graphs that do have negative cost cycles? In this short video, we'll see how to extend the Bellman-Ford algorithm, leaving its running time essentially unchanged, so that it can easily check whether or not the input graph has a negative cost cycle. So the following claim is going to indicate the appropriate extension of the Bellman-Ford algorithm. In particular, this claim characterizes the presence or absence of a negative cost cycle in the input graph in terms of behavior of the Bellman-Ford algorithm. Okay, well actually the Bellman-Ford algorithm, if we ran it for one extra iteration. So currently we stop the Bellman-Ford algorithm when the outer index I is equal to n minus 1. For the claim, we're going to envision running that outer for loop for one extra iteration when I equals n, running the same old recurrence for all of the destinations V. So the assertion then is that G, the input graph, has no negative cycle if and only if we don't get any new information from this extra batch of subproblems. That is, if and only if ANV is exactly the same thing as AN minus 1V for every possible destination V. Equivalently, the input graph does have a negative cost cycle if and only if there exists some subproblem, there exists some destination V, where we see an improvement at V by running the Bellman-Ford algorithm for this extra iteration. So we're going to prove the claim in the next slide. It's not too hard, but I hope it's immediately clear what the implications of the claim are, how we check for a negative cost cycle. So now, given an arbitrary input graph with no promises, it might have a negative cost cycle, it might not. What do? You run Bellman-Ford, but you run it for one more iteration. You run it for the outer for loop index I going all the way up to n. And you check, does some subproblem value change in that final iteration or not? If not, if all of your AN minus 1 V's are the same as your AN V's, then by the claim, you know there's no negative cost cycle. By our previous work, we know the Bellman-Ford algorithm is correct. So we happily return the AN minus 1 V's as the correct shortest path distances as before. If, on the other hand, you notice that there's a vertex V, so that ANV is different, is smaller than AN minus 1V, then you say, hey, there's a negative cycle by the claim, so I'm not going to compute shortest path distances for you. That wouldn't make sense. There is a negative cost cycle, and you punt. And of course, this one extra iteration in the Bellman-Ford algorithm has a negligible effect on its running time. It's still big O of m times n. So I'm lying a little bit in this claim. There's an edge case I'm not handling properly. When I wrote down the claim, I was thinking about arguably the common case of input graphs G, where there exists a path from S to every other destination V. That is, input graphs where all of the shortest path distances are finite. So if that's not the case, then the claim as stated is not correct. One way to see that would be just a degenerate instance where the source vertex S has no outgoing arcs at all, and maybe the rest of the vertices form a negative cost cycle. In that kind of graph, the left-hand side of this claim is false, but the right-hand side of this claim is satisfied. So to modify it for graphs that may have some infinite distances, I'm just going to modify the left-hand side to say G has a negative cost cycle that is reachable from the source vertex S. Now, if you actually wanted to detect in the input graph whether there was a negative cycle at all, reachable from S or otherwise, there are various tricks you can do to solve that problem, again, using the Bellman-Ford algorithm. So, for example, given an input graph, you can add a dummy sort of fictitious extra vertex and add arcs from that vertex to everybody else with length 0, run Bellman-Ford on that graph, and that will detect a negative cost cycle if one exists. So now that we know why we want the claim to be true, let's understand why it is true. Let's go to the proof. So the claim asserts something that's if and only if. On the left-hand side is the property of the input graph having no negative cost cycle. On the right-hand side is the property that the Bellman-Ford algorithm does not make any changes if you run one extra iteration. So proofs like this have two parts. Assuming the left, prove the right. Assuming the right, prove the left. One of these two parts, if you think about it, we already did when we proved that the Bellman-Ford algorithm is correct for graphs with no negative cost cycles. That is, if the left-hand side holds, if the input graph doesn't have a negative cost cycle, we already argued that you don't have to run the outer for loop beyond I equals n minus 1. That's sufficient to capture the shortest path. So in particular, take I as big as you like. For example, I equals n, you're not going to see even shorter paths. You're going to get exactly the same subproblem solutions. The content then is the reverse direction. So let's assume that we run Bellman-Ford, an extra iteration, and none of the subproblem solutions change. Now, I warned you there was this edge case when the input graph doesn't have a path from S to all other vertices and you have infinite distances. I'll leave those details to you. So let's just focus on the case when there is a path from S to everything else. And in particular, these subproblem values are going to be finite. So a little notation, I'm going to use lowercase d of a vertex v to denote the common value of its subproblems in the final two iterations, when I equals n minus 1 and when I equals n. So now the plan is we're just going to stare at the formula that we use to evaluate these subproblems. It's right there staring at us in the pseudocode for the Bellman-Ford algorithm. From that, we will get an inequality relating these d values to each other. And from that inequality, we will be easily able to deduce that every cycle of the input graph is indeed non-negative. That's the left-hand side of the statement. So what formula did we use to fill in this extra iteration of the table, the ANVs? Well, we just took the better of, on the one hand, AN minus 1V, the solution for the previous iteration, and then also the best of the candidates that use a last hop WV and concatenate a path with the most n minus 1 edges to W along with that edge WV. Let's also note that with our new notations, these little d values, the common value of a subproblem in the n minus 1 and nth iterations, we can write the left-hand side of this formula as d of v, and in the case 2 subproblems, we can write a n minus 1 w as d of w. Now, because the left-hand side of this equation is a minimum over a bunch of candidates on the right-hand side, if we zoom in on any one candidate on the right-hand side, so any choice of this last hop WV, we get something which is at least as big as the left-hand side. Again, the left-hand side is the smallest of all of the candidates. So in particular, for a given choice of the last hop W comma V, we get that d of V is at most d of W plus the length of the edge from W to V. Really, all this inequality is saying is that one way to get a path from S to V is to take a path from S to W and concatenate the final hop W comma V. The shortest path to V can only be better than this one particular candidate that goes via W. Now remember what it is we're trying to prove. We're trying to prove that the input graph has no negative cost cycles. So let's just pick our favorite cycle, capital C, and show that it has non-negative cost. This is going to be a sneaky application of the inequality that we just wrote down in pink. Specifically, we're going to sum that inequality over all of the edges in the cycle. It's going to be clearer if I just rearrange that pink inequality a little bit. So now let's look at the sum of the edge lengths in the cycle capital C. Remember, this is what we want to prove is non-negative. So we sum over the edges W comma V in big C, and for each edge we look at its cost, little c of WV. By the pink inequality, we can lower bound this by a sum over the edges in the cycle capital C of the difference between the d values of that edge, the endpoints of the edge. Notice that for a given arc WV on the cycle, the tail of this arc W, its d value appears with a coefficient of +1, and the d value of the head of this arc V appears with a coefficient of -1. But cycles, of course, have the very special property that every vertex of the cycle appears exactly once as the tail of some arc and exactly once as the head of some arc. So each d value of a vertex on the cycle is going to appear once with +1 coefficient, once with -1 coefficient. So when we get massive cancellation, we're left with just 0. So the cycle capital C has non-negative cost. That was an arbitrary cycle, so it's true simultaneously of all of the cycles in the input graph. That's exactly what we were trying to prove. So again, the presence of negative cost cycles in an input graph is characterized by the behavior of Bellman-Ford in an extra iteration. That's why it's easy to extend the basic algorithm to check negative cycles without affecting the running time.